the very good weld joint properties. Now, come to that next other topic, that is the phase transformation. So, we will try to look into some overall idea of the phase transformation, and it is very specific to the welding process and very specific to few materials. So, we have some idea about the phase transformation, that means there are three different way we represent the different diagram the phase transformation in case of metallic materials. So, first is the equilibrium phase diagram. Normally, we try to represent the binary alloy system. So, two alloy, assume that the material is the consists of the two alloy, and we can draw the equilibrium phase diagram for this alloy. So, equilibrium phase diagram is basically drawn at the almost theoretically the rate of the cooling is almost 0. That means, we try to follow the equilibrium condition of the phase transformation. So, that means there is almost no effect of the time here, that means we can neglect the effect of the time in this case. But if you look into the other diagram, the time temperature transformation diagram, we represent the different phase transformation line with respect to the axis, as a one is the temperature axis, another is the time axis. Similarly, in case of the continuous cooling transformation, that means that is called the CCT diagram. Here also we can plot that the transformation diagram following the constant cooling rate of the constant cooling rate, and here one axis represents the y axis normally represents the temperature, and x axis represents the time here. So, these are the three different diagram we normally use to explain the phase transformation, and in case of the mostly alloy element, and we are assuming all these cases we are assuming that it is a binary alloy system. But the equilibrium phase diagram is mainly to know the what is the phase presence there, but time temperature diagram is the transformation of the phase at constant temperature, which is most of the cases not practical, because and practically the transformation happens not as a constant temperature, rather there is a variable temperature. That means, the variable temperature can be better represented as a in terms of the cooling rate, constant cooling rate. So, that to represent the transformation using the constant cooling rate, that is better represented in the diagram of the CCT diagram. So, most of the heat treatments actually follows the CCT diagram to find out what is the final microstructure, depending upon the what is the cooling rate is followed during the process. It may be solidification process or it may be welding process. So, now if you look into the welding process, it is actually subjected to the any like other practical process subjected to the variable cooling rate, also variable temperature. So, but till we can use the phase transformation diagram, a CCT diagram or TTT diagram to explain the transformation of the different one phase to another phase with respect to time, with respect to temperature, with respect to the different fixed cooling rate. Now, melt zone, that means oil pool molten zone is basically subjected to the solidification, but heat affected zone solidification means here the transfer from the solid liquid phase to solid phase, but heat affected zone it is in solid state, but maybe solid state, but one phase to another phase transformation may happen. That means, it is a solid state phase transformation happens in the heat affected zone. So, this the typical overlook of the phase transformation we observe in case of the welding process. Now, we have tried to represent the phase diagram, because this phase diagram is helpful the composition of the different phases exist within the microstructure. So, here I just try to represent the iron carbon equilibrium phase diagram. Here you can see that y axis represents the temperature, that means at different temperature what is the different phase presence, and the x axis represents the weight percentage of the carbon. That means, it is a binary alloy system. Here the one component is the iron Fe and another component is the carbon. So, when Fe and carbon are mixing up to certain position, and depending upon the temperature different phase presents. For example, the phase boundary is represented here also. So, that gamma it represents by the austenitic, this is the austenitic phase. So, that means with this iron along with the different percentage of the carbon, the constitutes austenitic phase at the different range of the temperature. So, then another phase is the alpha ferrite. So, it is only ferrite or sometimes it is called the alpha ferrite. So, alpha ferrite, here we can see the alpha ferrite phase exists, it is a very low the percentage of the carbon. Basically, that carbon is the here the maximum solubility limit of the carbon within this phase produces is I think around 0.02 percentage of the carbon. So, that constitute the one phase, depending upon the that phase having the secondary second alloy, that means here is the carbon up to certain percentage, and they constitute one single phase, alpha phase. So, that is the alpha phase, and this alpha phase is having the some maximum amount of the solubility of the second phase, that means carbon here. Next, the other phase, the similarly austenite is the single phase structure, that means single phase structure, but it is having the maximum solubility of the certain carbon percentage exist in austenitic structure also. Now, if you look into the other within this phase boundary, and this phase mixture exists alpha plus gamma, that means ferrite, it is a this zone represents the mixture of the ferrite and austenite, and here is the beta phase is basically cementite. So, this is a one phase, the maximum solubility of the carbon in the cementite phase is the 6.67 percentage of the carbon, and they constitute one single phase, that is called the cementite. So, this phase here at this position, here the mixture of the two phase exist, the beta phase and the gamma phase, that means austenitic plus cementite phase mixture, and here you can see this zone two different phase, the ferrite and the cementite fixtures, but there is no existence of the austenitic phase this at this zone. That means that zone means it is defined over the certain temperature range. So, if we know for a specific binary alloy system, this phase diagram we will be able to find out from this phase diagram that coexistence of the single phase or mixture of the two different phases over the temperature range, we will get all kind of information from this phase diagram. But here this phase diagram is can be utilized if you see that with this phase diagram is no longer, it is equilibrium phase diagram, it is no longer related to the time component. So, therefore, rate of the cooling, all these things is having no importance here. Here we can constitute the if one phase mixture, if we know that one phase mixture, we can using the Leber rule we can find out what is the proportionate way the different phases exist within the mixture of the phases. So, that kind of information can be well extracted from the phase diagram. Anyway, if we look into that in the welded structure, so information of the welded structure, what are the different phase transformation may happen, or how it can be predicted in the final structure with respect to the type of the material or composition of the material. For example, first if we look into that stainless steel SS310, normally the nickel content is high in this type of the stainless steel. So, this final microstructure consists of the different phases like that primary austenite, dendrites and interdendritic delta ferrite between the primary and secondary dendritic arm. So, delta ferrite structure is also there, and the austenitic phase and the ferrite phase also there, but the delta ferrite mainly exists in the primary and secondary dendritic arms. In that spaces we can find out the delta ferrite. So, this consists of the two different phases, the delta ferrite and the austenitic phases, but they coexisted and making a homogeneous structure. Next, if we look into the material stainless steel, that high chromium SS309, that is chromium content is very high in this case as compared to the nickel content. So, this microstructures consist of the primary consists of the primary lath type delta ferrite in an austenitic matrix. So, that means overall structure is the austenitic matrix. So, within the austenitic matrix the delta ferrite exists in a type of lath. A lath type delta ferrite exists within the structure. So, their microstructure is maybe different from the SS 310, although both the cases the phases, austenitic phases as well as delta ferrite phases exist, but the distribution of the delta ferrite, the shape and size may be different in these two cases. So, normally the solid redistribution during the solidification is basically reduced and in presence of the high cooling rate, because at very high cooling rate probably the transformation of the one phase to another phase chances are, or transformation time is very less, probably that may be the reason for that redistribution during the redistribution of the different solid constitute or solid phases within the structure is basically reduced at very high cooling rate. And for this type of material specifically high cooling rate, at the same time for the low chromium and nickel ratio. When the chromium and nickel ratio is very low, in this case the redistribution of the solid phases can be reduced at high cooling rate. But if the chromium and the nickel ratio is very high, so in this case the delta ferrite is as the primary phase and the secondary, and their ferrite content actually increases with increasing the cooling rate. So, delta ferrite, if the chromium and nickel ratio is very high, in this case the delta is the primary phase is the delta ferrite, and the ferrite content is basically increases with increasing the cooling rate, because the transformation from delta ferrite to the austenitic transformation having the less time to occur is basically high cooling rate. So, if we see that normal, if we look into that, like this type different type of the material, their different phase exist within the microstructure, but the phase, that formation of the primary phase, secondary phase, it depends on the ratio of the other alloying elements. So, just this is one example, that if nickel and chromium is the main constituent for the stainless steel, if their ratio are different in these two cases, we can expect the different kind of the microstructure. So, of course, in this case we need to the in depth study of the different type of the microstructure for other material. Here we try to like another example for the weld microstructure in case of the low carbon steel. If you see that in low carbon steel, that austenitic phase is cooled down from the high temperature, and it called the alpha ferrite basically nucleates specifically at the grain boundary and specifically from the Widminstone pattern. So, specific pattern actually it forms when austenitic cool down to the from the high temperature to the low phase ferrite phase. So, at low temperature it is too slow for the Widminstone ferrite structure to grow to the grain interior. So, in that case acicular ferrite nucleates from the inoculations. So, this low carbon steel is basically forms the different type of the structure that actually that is called the grain boundary ferrite structure, polygonal ferrite structure, Widminstone pattern ferrite structure, acicular ferrite, upper bainite, lower bainite. So, this type of the different kind of the structure can produced by the weld microstructure, or we observe in the weld microstructure of the low carbon steel. Similarly, if you look into the CCT diagram, continuous cooling diagram for the 434 type of steel, we can find out that at the different range of the cooling rate, if we follow, we can find out the different structure. So, it is a very high cooling rate, probably you can get the martensitic structure, further less of the cooling rate bainite structure, very low cooling rate, gradually you can ferrite and pearlite or some mixture of the ferrite and pearlite. So, all this kind of structure we can expect in low carbon steel, but this the CCT diagram in this case is used to define that if we follow the different cooling rate, then we can expect the different kind of the structure. Of course, this structure maybe changes the if the composition changes in even in case of the low carbon steel, or maybe alloying elements change low carbon steel, then probably we can get the other kind of the structure, or there the one phase is distributed in different shapes within the other phase, that all can produce the different type of the microstructure. So, all can be depend or explained in terms of the rate of the different cooling rate. So, that is why it is very important to estimate during the welding process, or it is most of the cases we can find out the rate, the link between the rate of the cooling and the typical microstructure, and finally, that microstructure can decide the what is the mechanical properties of the weld joint, but the link between all these three components is not very straightforward or may not be linear always. So, it is a always exists the non-linear relationship. So, that relationship is varies depending if there is a change of the alloying elements. Now, next topic we will try to look into that solidification cracking, that is more related to the in the welding process. We see that cracks normally occurs during the welding of the regions. That first is that during the solidification process the crack occurs maybe due to the temperature gradient. So, if there is the existence of the temperature gradient, that also brings the thermal strain. And next possible reason for that is the compatibility of the different phases due to variation their compositions, and third, embrittlement of the grain boundary. So, sometimes the if grain boundary becomes embrittled, that actually induce the kind of the solidification thing, and another reason for the volumetric contract during the cooling process. So, different phase having different constitutes. So, it is not necessary that during the cooling process there may be the contraction of the within the there is a change microstructure due to the changes in the microstructure, there may be the contraction in the volume, that actually may induce some amount of the cracking phenomena during the solidification process.